Hi, my name is Paul Whitehead and I've been responsible for putting together the water quality programme within Marius, and it's been very much a team effort with strong support from people in CH, Alex Elliott, Mike Bowers and Dan Reid in particular, a team in Oxford, and also colleagues in Bristol, Nicholas Houghton and Gemma as well. So, although we've had a national perspective, which has been led largely by the Bristol team, we've also had a kind of a southeast focus with a particular emphasis on the River Thames catchment. The reason for this is that we had very good collaboration with Thames Water and the Environment Agency, and it was a case study, if you like, to look at how drought, low flows interact with water quality and ecology. We set up a model for the whole of the Thames systems. This is what we call the INCA model, Integrated Catchment Model. It kind of simulates both flow, but it also simulates water quality. In particular, we modelled nutrients, nitrogen, ammonia, pollutants, phosphorus, modelled sediments, different sediment fractions. And we've also constructed a new model to simulate phytoplankton growth within the river system. And this is using a completely unique data set that Dan Reid and Mike Bowers have developed, a new piece of technology which I think is a bit of a breakthrough technology because it can actually measure phytoplankton species in great detail and very, very rapidly. This is a bit of a game changer, I think. Anyway, it's provided an amazing data set with us to develop a new model of phytoplankton down the river. The model basically is spatially variable, so we have 22 different sites down the river, so we can simulate daily time series of flow and water quality at different points down the river, and therefore abstract data for example, the Farmwell Reservoir and lower down at the abstraction sites in the lower Thames, which can feed into Mohammed's water resources model. Water quality, we know, is significantly impacted by drought. Low flows affect water quality in several ways. Because you've got less water there, you've got less dilution of effluents, so you see increasing concentrations of nutrients, nitrogen, phosphorus, and that can impact the ecology in lowland rivers. Here you see the tennet, nice ranunculus growing on the left, on the right, typically what you see in a low flow condition, decaying macrophytes, due to the build-up of epiphytic algae on the macrophytes, which are stimulated by the light, the temperatures, and the high nutrient levels. And of course they then damage the river. People don't like to see rivers in that state. It also affects the fisheries and the ecology. The lower graph shows dissolved oxygen. And you can see some periods you get very, very low oxygens, which are during these high, these sort of low flow conditions, and you've got big build-up of macrophyte deaths basically will contribute to the organic loading, and that lowers the oxygen levels. And of course, you can get fish kills during these periods as well. The other thing about water quality is that there is a big post-flush effect. So at the end of a drought, you get a flush of material coming off the catchments, high flush of nitrogen, nitrates coming off, and sediments. And in the upland, peatland areas, you get a big flush of dissolved organic carbon as well, which can create problems for utilities, public water supply, where you've got high DOC levels. So drought has kind of quite big impacts on water quality and hence on water resource availability. And here's a sort of typical post-drought flushing effect. As soon as the catchment's wet up, you get this flush of material coming out of the catchment system. What we've done within Marius is again make use of the weather at home data. We use that to create, to look at time series of low flow periods. We can capture, as Gemma said, there's hundreds and hundreds of different time series there that we can select from, and we can basically run baselines of low flow conditions and near future and far futures through the model, and that generates time series of outputs of nutrients and sediments and water quality at different points down the river system. And then we can take the outputs of those and look at them in terms of probability, how how might the risk of damage to the river system be affected by future low flows in climate, and also provide information for the water resources model. One of the really interesting things is looking at this, how this interacts with the phytoplankton. I won't go into great detail on this, but if you look at the fourth slide along, that's cyanobacteria, which is a particularly nasty toxic algae growing in our rivers. The black cloud at the bottom is the UK SIP09, which is sort of the spread of climate, if you like. And when you focus on the low flows, you see it shifting up to that red zone. And what that means is that you're going to get increased populations of cyanobacteria in the river system, if you believe the models. And there's some evidence from Mike Bowers and Dan Reed's data sets that you are seeing cyanobacteria improvements in rivers like the Thames. And there might be other issues like diatoms, for example, that might affect intakes to water abstraction plants. So what are water quality results? There's been an awful lot of information that's come out of this. We've talked about drought reduction and low flows. You do get an interesting sort of biochemical effect happening in rivers where under low flows there's more residence time, so the denitrifying bacteria can, if you like, convert the nitrate to nitrogen gas and nitrous oxide. So you get what you can see a reduction in nitrate concentrations in the low flow periods, but you are generating more greenhouse gases, which is quite an interesting side effect. The phytoplankton response varies, dissolved oxygen varies, there are sediment flushes coming out, and there's this upland DOC flush. So a lot of factors, a lot of water quality issues can arise out of low flows and droughts.